Hello everyone, this is Madi Neysar Mogaddasi. This is the Open Food Fact project for CS5331. Outline of the project update is as follows. The pre-processing, which is about discussing data analysis as well as the data cleaning of the progress that I have so far. The data that I've gathered from the Kaggle website is about 900 megabyte data in the format of a tab-separated file or TSV. As a part of the data analysis, I gather about 160 features, which is more than 200,000 observations included in it. Out of these 160 features, which are included in the format of text and numeric data, only 80 features will be numeric and also providing helpful informations for the next step that I will discuss. I noticed that the data that I'm working on is very much sparse, meaning about the 40% of the data is included with NA or missing informations. As a challenge, I was not able to using the function omit to removing the old data because it will lead to finding an empty data sets. To overcome this challenge, I was able to removing the columns out of those 80 features that has more than 20% missing data. It was end up with about 16 column or 16 features that I will start working on different algorithms with them. The output that is showing in this slide showing that 16 features or 16 columns that after removing the missing data will be the output of the previous section of the algorithms. Having these 16 characteristic or 16 features, the next step I will use them to finding a group of foods that having the similar characteristics based on this particular columns that is being discussed here. For example, as we briefly look at it, most of these features are somehow related to the nutrition facts, such as the level of the vitamin, calcium, and iron for that particular food that is the data that we have representing that level of those particular nutrition facts. So the next step that I'm working on is to finding and clustering these foods and providing several topics or several groups that having the foods with similar nutrition fact. After cleaning the data, the next step in this project was to perform the data clusterings. The goal of the data clustering is to finding the common object, or in our example common product, that have the similar features, which in our case is that they're having a common level of the vitamin or protein in one group. So basically what we want to do in this project is to come with a set of the groups that putting the different products in a separate group, while each group has the similar characteristic in each other. As a part of the clusterings, I pick K-mean algorithm, which is one of the most common algorithm across researcher and then academic areas to perform the clusterings. I picked K-mean because it's robustness and as well as it's easy and available support in the R programming language. Before starting to performing the clusterings, K-mean, the K here is representing to the number of the clusters. So I need to finding what will be the an optimal value for the set of the cluster or groups that I want to basically find in these data sets. I use the ELV method, which I will discuss in the next slide, to finding this optimal number of the clusters. And after performing the clusterings, I use the silhouette measurements to finding that how well this clustering has been performed. So in the basically the ELV method is one of the algorithms that been used to finding that what will be the optimal number of the clusters. Is basically calculating the sum of the squares, and once the curve that is basically, as an example is showing in this slide, once the curve is start breaking and going at the smooth line, that will be most likely one of the breakpoint or critical point that we use as a number of the clusters. This slide in this particular diagram, if you pay attention to the breaking point, you will notice that it's not as smooth as it should be. This is due to having the number of the outliers in our data sets. Before running this ELV method, one of the things that I had to do on the data sets was to finding out what will be the outlier and removing them. That was one of the steps as additional steps that comes after the data cleaning and before the actual running the clustering came in to finding the optimal number of the clusters. If you're looking at the next diagram or next figure, you will see that it's more smooth after the number of after 10 clusters, or once it goes to the 20 and so on. And this is because this data, this sum of the squares, has been calculating on the part of the data sets that doesn't have any outlier. So this is more suitable to ELV method and for this particular project to know that when would be the starting point to finding this optimal value. In this example, I picked 10 as a value of the k, which is representing the number of the clusters. For the implementation in the K-mean, I used two libraries for this purpose. The FPC libraries helped me to basically having a visualization of the ELV method to finding what will be the optimal value for the clusters. For the actual K-mean implementations, meaning that the actual performing the clusters, I picked the class libraries, which is one of the robust classes in R. The way that the K-mean is working is to finding a number of random point or random object across a data set, which we call it as a centroid, which sometimes this random point is keep changing by finding that what will be the center of mass from the geometric perspective in our data sets, and then calculating the sum of the square error of the different points to this particular centroid or medioid. Once this number, this is basically sum of the square error, get minimized, the cluster will basically created. This implementation has been executed on a laptop with 6 gigabyte and a processor of i5. The output of the K-mean algorithms is set of the clusters that from the geometric perspective there should be a neighborhood, a boundary basically between each clusters. From the algebraic point of view, if we want to evaluate this basically result or this set of the cluster to know that how well we are clustering on these data sets. One of the ways is using the silhouette coefficients. This coefficient has a range between -1 to the +1, where the more that the value is close to the upper boundary, meaning the +1, it means that the data is being well clustered. However, if the values of this coefficient is more close to the -1, it means that there might be more points that are basically clusters across the several groups. In this project, the value of the silhouette coefficient was -0.8. From the metrics perspective, it shows that though this is not very justifying that there is very well distinguishing clusters across the data sets, but it shows that we were able to finding basically range or a boundary that establish a neighborhood across this set of the clusters. The FPC library providing a plot mechanism that using the PCA under a hood, meaning that only two features that has the highest variance will picked by the FPC class to be visualized after the clustering has been performed. As it is showing in this particular plot, there is a very high density of the data for these two features that has been selected, that it was not easy for the k-mean algorithm to distinguish a set of the clusters. What it means from the perspective of the business domain, that the data that we have, which is a set of thousands perhaps products, has a very common vitamin level or different attributes that very much will not be easy to distinguish. If you want to having another basically judgment of the data, we can say that this set of the data that has been analyzed perhaps belonging to the one specific or maybe a few specific categories of the foods. For example, it could be snacks, or it could be the vegetable, or any specific particular food products that has a common attributes. So the result will be a dense plot or dense data sets that though we would have a clusters, 10 clusters out of this data set, but it will not be very well distinguished or having a very well boundaries between each other. As a part of the conclusion for these projects, there are a few points that need to be discussed. First of all, the result of this project shows that the dataset that we have lead to a density clusters, meaning that this particular dataset that we have doesn't include most variations of the different categories of the foods. For example, in the reality, the data that could basically use could have different vegetarian sections, meat, conserve, and other products. So in that case, you may notice a different level of the vitamins and then proteins and so on and so forth. Since these basically attributes doesn't have the enough variance, the output of this project shows that there is a very dense clusters that make it very difficult to finding the neighborhood or the boundary between each clusters. Although it may not be very applicable to finding out this set of the groups, but the output of these projects definitely can be used as a core for recommendation engines in such a way that once it's a particular product in an e-commerce website has been picked, we can looking at to finding that particular products in the clusters, and a similar items or the product can be also suggested to users. So this is a very good examples of having a core systems that in its backgrounds is using the output of these projects. Also, furthermore, this will providing dietary guidelines for the people who wants to trying the different variation of the foods, but they want to making sure that the level of the protein or the level of the vitamins of that particular nutrition that they are followed are very close to the food that they are used to have it in the daily. Using the output of these projects, they can finding out that particular diet and following the different products of that particular clusters. Hopefully, this will providing establishments for the future research in this area. Thank you very much for watching this presentation. If you have any questions or comments, please send an email to my email address at madi.muqaddasi@ttu. Thank you.